So thanks for listening my lecture regarding plane waves, and the course is still optics. And I felt that maybe in this stage, before I actually start my lecture, I will be spending a few minutes on motivation of the rest of the lectures on this chapter, because we are now really changing our mathematical treatment quite a bit, since we are moving to describe waves in a real three-dimensional space. So we are expanding our mathematical framework, and then we are also, for example, adding a possibility that we will have a polarization in our wave description. So we also are changing our amplitude of the field to be a vector valued quantity, so that we will be generalizing our mathematics quite a bit. And since vectors are nowadays, you students are not as comfortable and familiar with using vectors as people have used to be back in the 70s, is that I guess it's better that we will go in small steps. You don't need to go, well, in the end, using vectors, doing calculations using them, it's not that difficult, but it just takes a little bit of time and practice. And the kind of reward that we get when we are dealing with vectors properly is that we can really describe quite arbitrary things, and in the end in a quite nice notation. So we will be, in this lecture, I will be generalizing our treatment into plane waves, so that I will be showing you how we can have a plane wave that is propagating in an arbitrary direction, now defined by the wave vector k. After that, in 3.8, I will be generalizing the wave equation in all these three dimensions, so that how that is being generalized, not just with respect to one single coordinate, but in all 3D space. And then, of course, these plane waves that we will be introducing, they fulfill these more general wave equation. And then in 3.9, I will be speaking of other possibilities as the kind of primary waves. So instead of plane waves, in some cases, it makes more sense to describe things using spherical waves or cylindrical waves. And here in 3.10, we introduce polarization. So in essence, we replace the scalar valued amplitude for the field. It can be a real valued amplitude or a complex valued amplitude, as we have just discovered, but nevertheless, it has been a scalar valued number. And now what happens when we have a vector valued field amplitude? And then we start progressing towards the kind of possibilities of introducing to you the Maxwell's equations in all their glory in a vectorial form. So we will have a tutorial on vector calculus. Calculus here, of course, just means that we will introduce to you the operations that we can then use to differentiate vectors, or in principle how we could integrate vectors. But mostly in here we are just interested in differentiating vectors, vector-like quantities. And finally, this slightly goes off topic in terms of optics, but I will be speaking at the end of electrostatic approximation and the potential formulation, so that this I felt is a pretty good exercise then for us to kind of show how we are dealing with these vector waves and the vector calculus before we actually go into the Maxwell's equations in the next chapter and next week. And here, okay, in this lecture, let's now get started for the actual main message I want to say on this one, is that I will be introducing to you a plane wave, and now instead of just propagating along the z direction, I will now allow this plane wave to actually propagate in arbitrary direction. And in this case, we really need to generalize the wave vector k to be a vector quantity, and then it is this wave vector k that gives us the direction of propagation of my wave, plane wave. And then I will be speaking about the phase and phase front of this plane wave, and show that it will be a kind of plane where the phase of the wave is constant, and this is really defined by the wave vector k. And I will be showing you the mathematical way to describe these kind of plane waves, and we will repeat our original way of defining the wave number, so that how we can actually then get again the result that the amplitude of the wave vector k, or the wave number k, equals 2 pi over lambda. So I will show that in the case when we actually have a wave vector that is a vector quantity, it's the amplitude of this vector that is the wave number. And then I will be repeating the calculation of the phase velocity, but now I will be showing that in the case of a plane wave, like things can still be reconciled, and still, even in 3D case, the plane wave propagates at the speed of light inside that medium. So this is what I will be speaking on this lecture. And let's now get started. So like I said already, we have so far only considered wave that propagates along a single spatial coordinate, z direction. Of course, we could rotate our coordinate system, so this z can of course be slightly arbitrary, but especially if you would want to deal with waves or several waves that would be propagating in slightly different directions, we cannot just rotate the coordinate system for all of these waves, but rather we need to come up with a mathematical description that we can use to describe waves propagating in arbitrary direction and not just along z direction. And this is the kind of motivation. We need to generalize our treatment to a three-dimensional space because this is the kind of space we're living in. And how do we do that is that we now assume or we take the wave to propagate along an arbitrary direction, and we say that this direction will be now defined by a wave vector k. Now we just do not need to know anything about this k, how does it look like, but we just assume we have a wave and it propagates along a specific direction, and this direction is defined by this wave vector k. And of course, since we are dealing with physics and a physical system, the wave and its properties cannot really depend on the choice of the coordinate system. So no matter in what kind of coordinate system we are looking at our same wave quantity physically, it should be the same kind of quantity if it would be representing a physical occurrence, a physical wave propagating in space. And what this implies to us is that now the phase evolution must depend linearly on the position r. So the phase evolution must be exactly the same kind of phase evolution that we had with the exponent I, k, z term. But now, since we don't have just a propagation along the z direction, but rather along from point 0 to position r, we must have a subsequently same kind of phase evolution along this arbitrary direction. And then part of the wave that is in a plane that is perpendicular to this direction propagation, so this wave vector k, then this should have a same phase, this plane perpendicular. And this kind of plane is also known in our optics slang as a phase front, and this should be a constant valued function. So when we are looking of the wave in the plane that is exactly perpendicular to the direction of propagation, the phase front should be a constant. So the phase should be a constant valued. So this is what we require for the properties of the wave. And let's now see into what kind of math these two requirements leads into. So we ensure that the properties of the wave remain unchanged when we consider a plane S that is perpendicular to the wave vector k. Since the phase should be constant, then its properties should not be changed. So in essence, what we are now having is that we are having like a wave that looks like a plane, and hence it's called a plane wave that is propagating along the direction of k, and we require that the properties of the wave are constant in this plane. Here, since we are not dealing with a polarization of the wave yet, and mostly the only property that must be the same is the amplitude and the phase. So that's what is constant in this plane, and mostly here we will be just thinking about the phase front, and the phase of the wave in that plane should be constant. And let's now, how do we ensure mathematically that we can have this kind of plane where the phase is constant? Well, we can define or redefine a position vector r0 that resides in this plane S, and we are stating that in this plane the wave should have a constant phase. And in this case, when we are looking at other points R in that plane, or that are inside in that plane S, we know that we must have a condition of this fulfilled. So we have R minus R naught, and when we take the dot product of K, this is the propagation direction of my plane wave, this must be 0. So this seems very, very far-fetched maybe in the beginning when you look at it, but what we have here physically is that we have a vector K, and this defines the direction of my wave. And then we want to mathematically see how we can define this plane that is perpendicular to this direction K. And how do we ensure that this is perpendicular, this plane? We take 2 points in the plane, so we take the R and R naught, and then when we would be calculating their difference vector, so basically a vector now in the plane, like if we require that the dot product of this vector here is 0, then physically the fact that the dot product gives us a 0 means that all these vectors must be in the plane that is perpendicular to K. So we take use of the properties of the dot product, and then we use that to construct our plane S. And this is a trick we often do in physics and math, and I guess in chemistry and every natural sciences, when we want to kind of somehow define things that are perpendicular to some direction. We can reshuffle these terms. So on the left-hand side, we can leave R dot product of K, and then on the right-hand side, we can have the R naught times K, and this now should be a constant, so that they will have the original condition fulfilling. And this, of course, will give us a fact that when we have the R and R naught in the right plane, then we have formed a plane that is perpendicular to K. So then what we require still is that the phase evolution of the wave that is propagating along K now should be linear along this direction of propagation along the K. So we can write the final wave into a form that we have the wave psi, depending on R. Well, I guess I should have a vector R in here in case for sloppy notation. So I have my amplitude and then exponent IKR. So this is my complex representation of the wave. And the nice thing here is that now inside the exponent, I actually have a K here, which is a vector, and I have my R here, which is a position vector, so that I can now actually use this to describe a wave propagating a given direction. And this, in fact, is a wave that we call a plane wave. And why do we call it a plane wave? Is that when we look at the plane perpendicular to the direction of propagation K, then its properties are constant in there. And it extends to all infinity, this plane wave. So of course it's only a mathematical quantity, not really a physical one, but it's highly useful in terms of describing how light propagates. And the trick we did here is, of course, that we required that this dot product is 0, and then we're just using the kind of graphical interpretation of a dot product. As long as this is 0, the dot product, then we know that the K must be perpendicular to the R and R prime. Their subtraction vector. Now let's consider how its properties, they should be the same as with the original case when the wave just propagating along Z. So let's look at the periodicity of this plane wave that propagates in an arbitrary direction. And again, of course, this kind of wave should also have a wavelength associated with it, and the wavelength should be the same as we would have the plane propagating along Z. So we should verify this at least. So the wave must repeat itself after a propagation distance of lambda. So this is a property the wave must have. And of course, now we are not propagating along z, but we are propagating along k. So what we should have is that there we have psi, and then this psi in a position of r, so the wave in the position of r, must be equal to the wave in a position of r plus a distance of lambda along the direction of the wave vector k. And we have the hat there, so that we have the unit vector length in here, so that we only have we have propagating only a distance of lambda along that direction. We can rewrite this, of course, that I'm just clarifying here that this is a unit vector along k, so that we can also write this unit vector as the original wave vector k divided with the length of that vector k, scalar k. So k hat basically is the vector divided by its modulus, and sometimes we just describe things, the modulus, using scalar k. So it's a unit vector along k. And now, just using complex notation, the above equality that we have, we just plug in numbers. So the original left-hand side point in the wave in the point r can be written like this. So it's the amplitude a times exponent ikr. And then on the right-hand side, we let the wave propagate a distance of one wavelength in the direction of k. So we have this on the right-hand side. And of course, we can get rid of the amplitudes a's. They can be subtracted, and we can then like have this guy on the other hand, on the other side. So we divide both sides with this term, and what's left is that on the left-hand side we have unity, and on the right-hand side what we are left is that we have the dot product of the k's times lambda divided by the k. And this, of course, like we can write that this is I k lambda. So when we calculate the dot product of a vector with itself, of course we have the length to the power of 2, and since we're like dividing with the length of the vector, what we are left is that we only have the amplitude of the vector left, and then ik lambda here. So mathematically, of course, like I tried to say about this condition, when you have the dot product of dot product of the vector with itself, of course we have the modulo square of the vector. And now, since we are in the exponent notation, exponent function is also a periodic function, so we are in equal condition that the k lambda must be an integer of 2 pi, so that the exponent would be a unity. So here, this is a complex valued number of length unity, but depending on the kind of actual phase of the complex number, it's not always the case that this condition holds. It only holds when k times lambda is an equal of 2 pi and an integer of that. And now the easiest case is to require that the integer m is equal to unity, because that gives me the kind of smallest possible k. Is that now I have k equal to 2 pi divided by lambda, and this is now again my amplitude of the wave vector. And this is of course what we already defined, that what is the k, and it's exactly the same, but now at least we have verified that even in the case of a general wave vector k, so now it's really a vector, the amplitude of the wave vector is the same kind of quantity as before, so the wave number. And now the final thing to do is that we are ensuring that the wave propagates at the same speed as before, so that this is what we will do in the end. We will be showing that the phase velocity is the same as before. So let's now add the time harmonic time dependence into the description of the wave, so that they really have same kind of quantity as before. And in this case, the wave function becomes of a form that we have psi, and now it depends on the position r, and it also depends on time. So we have the amplitude a, and then we have the exponent ikr minus omega t. So this is the kind of most general way of describing a time harmonic plane wave. So it's a plane wave, so we have this kind of term here, and it's time harmonic, so we have this kind of time dependence. And please note here, what we have inside the exponent, it's still a scalar valued number. So when we take the dot product of k and r, this gives me a scalar valued quantity. So please don't be confused that we would have something like a vectorial quantity or a matrix inside the exponent. So it will still be a scalar valued phase function. And this wave, really is a plane wave, so that the phase front of this wave is really defined as a surface, and it's really a plane-like surface, and the phase in this surface is really described by a single number. Of course, it can be a complex number, so that the relative phase can be something arbitrary, so that when we would start adding many plane waves together, it might be the case that they would have different relative phases. But yet again, in this plane, a single phase can be described using a single number. So that's the definition of the phase front. In other way of saying is that the phase is constant on the surface of the plane when we are dealing with plane waves. And finally, let's verify that the phase velocity Vp is the same as before in this arbitrary case of direction of propagation for the wave. And this time we just use it, we derive this using the concept of total differential. So the phase of the wave, that's the phase function phi. So we can still write this, that what's inside the exponent, that's the kr minus omega t, and this is the phase function. And I will just simplify this dot product here so that they what is the result of this dot product. I can just use a sloppy notation that I will state that that's the k times r along k, and the minus omega t remains unchanged. And now if I calculate the total differential, what is the kind of small change of the phase function, I can then write that this will be of a form of k times differential of r along the k direction, because k is constant when we calculate the total differential. And then here the second term is minus omega and dt. So of course here we calculate the total differential of the phase function, and k is a constant and omega is a constant for a time harmonic plane wave. So the total differential looks like this. And since we require that it's the phase front that propagates at a constant velocity, so we say that this total differential should be 0, because this then gives me a fact that the phi, the phase function, is a constant. Right, exactly the same kind of physical reasoning that we used before. And what this gives me is that then when I'm calculating the phase velocity, I'm calculating the derivative of rk with respect to time, I get omega per k as a result. So as before, we have the same kind of phase velocity, but now we have just verified it when the wave propagates also in an arbitrary direction. So in that respect, we did nothing else than to change our mathematical description from a wave that propagated along the z direction into a wave that now can propagate along an arbitrary k direction. But all the properties of the wave remain unchanged. And now when we have generalized the treatment that we actually propagating in an arbitrary direction, it also starts to make sense that we are also thinking of the phase front of the wave, and thus we are calling the wave as a plane wave. And in some cases, it really makes sense to kind of understand that the phase front is the plane where the phase of the wave is constant. So this is what we had today on this lecture regarding plane waves. And what we will be doing next is that I will be generalizing the wave equation, and then we could verify that these kind of plane waves fulfill also the generalized wave equation. But more on that, of course, in the next lecture. So thanks for following me, and bye-bye.